Okay, this is lecture 11, part 2. It will be pretty short. It's simply percent yield and then working with stoichiometry with energy. So very briefly, if you remember, we calculated, one of the things we do with stoichiometry is calculate how much of a product can you make with what you have. You're given a starting amount of material. This example is 7.95 grams of oxygen. How much of a certain product or each product can you make? And I said that is called a theoretical yield. That's your calculated yield. The actual yield, when you go in the lab and you take your 7.95 grams of oxygen and you combine it with, let's say you have plenty of excess propane and you get your calculated product, or you get your product, it's probably not going to be the same as the calculated, the theoretical, because in real life things happen that can affect the outcome, the yield, the amount of product that you make. Like I said, you could lose a little bit of oxygen or propane to the air. Maybe some of it's not consumed completely. There's just a number of little things that can happen. So we calculate what's called percent yield. And very simply, it's your calculated or theoretical yield, and you take your actual yield, divide it by your theoretical, times 100%. It's times 100% because it's a percentage. So I'll work this on the whiteboard. Okay, we have 2 to work on the whiteboard, but it's really a very simple concept, so won't go too much into it. Okay, so percent yield is how much of the calculated did you actually get. I mean, if you had 100% yield, then your actual equaled your calculated or theoretical. But we call the calculated theoretical yield in theory, not, and then times 100%. Because your 100%, I don't know if you can see that, this is a mathematical construct to get the percent. This does not count towards sig figs, only these numbers. All right, so 2 examples on the slides. The one says, and I think I went over this in class, so we have this reaction equation. Okay, and we calculated a yield of this. If you have 5 grams of bromine fluoride, how much oxygen can you make? We want to go through the stoichiometry of that. You have to first change this to moles. Remember, we cannot do any of these conversions until we're in moles. So you use the molar mass. All right, so actually I will work the whole thing down out here in one step. So 5.00 bromine fluoride. We're going to convert that to moles, right? And then we have to change, we're in moles now, so we have to change the identity, because the question was about oxygen, this guy right here that I'm running into. So we go to our reaction equation. Chromium fluoride is 4, oxygen is 3. We have to come down here because I've run out of room, because it asks for mass of oxygen. And again, I'm looking at the slides, so you have to change your moles of oxygen back to grams. Anytime you're asked for mass, that's grams. So when you do all of this, you end up with a calculated or theoretical yield, 0.876 grams of oxygen. Okay. I'm going to erase this because I have no room. So your theoretical yield I'm going to put on the bottom. I'll write it a little bit higher. .876. Okay, so that's what you calculated. You actually went into the lab though, and you did this experiment, and you got your mass of your final product was 672 grams. So you're going to calculate your percent yield. What percent of the theoretical did I get? Because it's percent, you have to multiply times 100%. Again, this does not count towards your sig figs. It's a mathematical construct, 3 sig figs and 3 sig figs. So if I do the math, I come up and it's 76.7%. And yes, your answer should be, your percentage should be in the sig fig rule. So this is 3 sig figs, that's 3. So my percentage is 3 sig figs. I'm not going to say 77%, it's 76.7. So that's all percent yield is. What you actually got divided by what you calculated, your theoretical, and then of course times 100% because it's a percentage. It's not a decimal. So the other example in the slide, and I'll have to go to the calculator because I actually haven't done this one yet. So this will be the second slide, and it's got multiple choice answers. And this uses our propane example again that I did lots of examples before. And in this propane example, the theoretical yield, I can't see it, with water was 3.58 grams of water in the propane experiment. But when you went to the lab, you only got 2.50 grams of water. So what is your percent yield? Right, you just divide your actual by your theoretical. So my actual was 2.50. My theoretical is 3.58. Again, it's a percent, so we have to say 100%, but that does not count towards the sig figs. So I get 69.8, that's an 8. 832%, 3 sig figs, the 0 on the end. It's on the right side of the decimal place. The only reason it's there is it's significant. 3 here, so my answer is going to be 3 sig figs. So it's 69.8%. And if you go back to the slide that I got this from, oh, this one, lost my place for a minute. Right here, and the answer is D, 69.8%. Okay. So that's very straightforward, and you just want to practice it. The last thing I wanted to touch on was stoichiometry with energy. One of the examples I worked out with the 200 kilojoules, we did this. I'm going to go a little further into it. Pull up my other slides. So we talked about a reaction being exothermic, endothermic. I know commonly you see these feels hot, feels cold. Personally, I don't like using that. I like to think of it more of what's actually happening at the chemical level, which is you're putting energy in to make the reaction happen, right? That's here. Your starting energy is less than the ending enthalpy. The H of the product is higher than the H of the initial of your reactants. So you have to add energy to make this reaction happen. If you have to put energy in, it's endothermic. Now remember, we have a system and we have a surroundings. Go to the board just for a minute. Well, actually, the next slide. So remember, we have a surroundings and we have a system. The system is the chemical reaction. So maybe it's a liquid reaction, so it's the liquid. The surroundings is the area around it and also the flask, the walls of the flask. So they exchange energy. If it's endothermic, energy goes into the reaction, but where does it come from? It comes from the surroundings. If I take heat energy away from the surroundings, the temperature is going to go down. The surroundings. To give energy to the reaction, to make that reaction happen. Otherwise, the reaction can't happen. If it's exothermic, your product energy is lower than your starting. So this extra energy had to go somewhere, right? Your difference. So it goes out into the surroundings. And this, by the way, is activation energy. That's the breaking of bonds. Every reaction has that. So what matters is your product, the difference between your product and your reactant. So if it's exothermic, this is my system. This is where the reaction is happening. It has giving off energy as a product, heat energy as a product, enthalpy. Therefore, where is that energy going to go? It's going to go into the system. It's going to go into the walls of the flask, the air around it. The temperature will increase of those because they are getting energy added to them. So this is the chart that we use to show starting enthalpy, ending for exo, and starting enthalpy, ending for endo. Okay. So remember, what's happening is the energy is being exchanged between the system and the surroundings. So you're going to look at that whole package and all of the energy is contained within it, but is it going from the system into the surroundings? That's exo. Is it going from the surroundings into the system to make it happen? That's endo. It's going in. We can calculate energy just like we calculate moles of our reactants and our products. One thing to notice, when we do a delta H is the difference between the product and the reactant. It's the product, the enthalpy, because there's an enthalpy total on this side. There's an enthalpy total on this side. So if this enthalpy is lower than this, your delta H will be negative. I mean, think of this as 1 and this is 2. It's product minus reactant. So if you go 1 minus 2, you're going to get -1. So your delta H is negative. That's excess energy. Your energy as a product goes over here. All of these in the reaction equation will have a plus, because reaction equations are saying this plus this plus this gives you this plus this plus this. So this isn't a sign thing. This is part of the reaction equation. The sign comes into the delta. Okay, so keep that in mind. The sign has to do with the delta, which means change. It's the product minus the reactant. If you had to put energy into it. That means that the product energy was higher than the starting energy, and therefore the energy you had to add to the reaction to make it happen. You had hydrogen gas plus iodine gas plus energy is how you made this happen. It's a reactant. It's one of the reactants. You had to combine these three things to make this reaction happen. You couldn't just combine the hydrogen and iodine, nothing would have happened. It needed the extra energy to kickstart it. So if it's endothermic, energy goes on the reactant side. But notice the sign doesn't, it's not, this isn't a sign thing when it's in a reaction equation. Everything in the reaction equation is plus, because it's not a sign, it's this plus this equals this plus this. This plus this equals this plus this, or just this. Okay, so delta H is product minus reactant. Delta H sign is negative for exo. Delta H sign is positive for endo. Endothermic, the energy is part of the reactants. Exothermic, the energy is given off, so it's part of the product. So we can use that energy just like we use any of the other molecules in our balanced equation. It's just that the unit is kilojoules or joules. It's usually kilojoules. Is the, you know, we're not using moles, we're using energy unit. Okay, I thought there were some examples here. Yeah, I think right there. So going through the questions just to refresh your memory about exo and endo. So if your reactants, your starting material, are higher than the products, the ending, what kind of reaction occurred? Well, products minus reactants is going to be negative. And so if it's a delta H is negative, then it's exothermic. And so the answer is C. And so for that says, for the previous exothermic reaction, what mathematical sign would we use to report the change? Change is delta. Change in enthalpy is delta H. And as we just said, that's negative because it's the H of the product minus the H of the reactant. And endothermic, you have to put energy into the system from the surroundings. What temperature change or changes would we expect? Well, the surroundings are giving their energy to the system. So the surroundings will get cooler. The system will not get hotter because the system is using that energy to create bonds. So the energy is not going into heat, it's going in to create bonds. So what happens in endo is the surroundings get cooler because the energy goes into the system, but it's going into there to make new bonds, higher energy bonds. And so that's why the system doesn't get hotter, is because it goes to for a different purpose. So the surroundings will get cooler in endothermic. So let's look at this question on the whiteboard. And this is how we're going to use energy in our stoichiometric conversions, you know, reactions, right? Stoichiometry, reaction stoichiometry with energy. So in this case, we have a delta H that's positive. Therefore, this is part of the reactant. I had to put 33 kilojoules of energy into this to make it happen. So you actually would put it over here on the reactant side, 2 ammonia gas plus 33 kilojoules yields. So you have to put the energy in this to split ammonia into nitrogen and hydrogen gas. So let's go to whiteboard. So the reaction, I'm going to put the energy in here because you have ammonia. If you don't put this 33 kilojoules into the reaction, it won't happen. Okay. It says how much energy, so the question is energy, will it take to convert 45.5 grams of ammonia, that's NH3, into N2. In other words, we have 45.5 grams that we are going to convert into the products. So what's the first thing you do when you see this in stoichiometry? The very first thing you should think when you see grams and we're doing stoichiometry is convert to moles. When in doubt, convert something to moles. You can't go wrong. Because we cannot do stoichiometry with grams. We have to do moles. So this is NH3 for 1 mole for 16.04 grams. So that will cancel that. Now we'll have moles. Okay, now I have moles of ammonia. Cool, we're on the way. What do we want? We want to convert it into nitrogen. Well, that's this reaction. Okay. It didn't say a certain amount of nitrogen. It just says, what energy do we need to make this happen? We're going to need 33 kilojoules of energy for every 2 moles of ammonia. So we put that relationship in just like as if the question we're asking for one of the products, for example, how much product can you make? It's how much energy do you need? So you do your relationship, your identity change. Moles of ammonia goes down here. Normally we put moles of a product up here. But since it's energy, we're putting kJ. So this is an identity switch, just like if it asked how much nitrogen can you make with 45.5 grams of ammonia. But this time I'm saying how much energy, well, how much of the other reactant will be consumed. So we're going to go, once we're in moles of ammonia, we're going to do our identity change and then we go to the reaction. Fill these numbers in from the reaction equation. How much ammonia? I have 2 moles of ammonia. For every 2, I have 33 kilojoules of energy. And then you just do the math, which they didn't do on the slide. So it's 45.5 times 33 equals, divided by 16.04 equals, and I get 93.61 kilojoules. And then let's go back and check sig figs. I have 3 here. I have 4 here. I have 2 there. That counts because that's a number that can vary. That's a value that was measured and entered. It's not an exact number like the stoichiometry. So therefore, I'm going to give my answer as 94 kilojoules. Okay. So you do the normal steps when you get to the change identity part. Instead of putting a mole of something up here, you put your unit of a kilojoule and then you put your numbers in from the reaction equation. All right, let's do the next slide. And the next slide has the big blue band on it. Remember, you can remove it in the regular slides, not the slideshow, but the regular slides. So we have this reaction equation. I am not going to put the phases in just because of limited space. But normally we would. And it gives a delta H of negative 3347 kilojoules. If it's negative, it's exothermic, which means it's a product. I know that's a negative, it's a delta. If we're putting it in the reaction equation, we're just saying this plus this plus this plus this. So you just keep, the plus is not a sign, it's just a statement of part of the reaction equation. Okay, so there's my reaction equation. And the first question is how much heat is liberated. So you can kind of think, how much heat do I make when 32.4 grams of, well, Fe3O4 is actually kind of iron 1 and 2 oxide, which don't get confused about that. Yeah. 32.4 grams of this reacts with aluminum. So you're saying, how much energy do I make when I start with this in this reaction? Very first thing, convert to moles, right? We know that. So 32.4 grams Fe3O4, right? Molar mass. And it is 1 mole for every 232. I'm looking at the slide. That will cancel out my grams. Okay, now I'm in moles of ferrous oxide, the iron 1,2 oxide. So now I have to change identity. So we get that from the reaction equation. In this equation, how many moles of ferrous oxide do I have? I have 3. How much energy do I have? I have 3,347. Okay, so 32.4 times 3347 equals, divided by parenthesis 232 times 3, exit parenthesis, you're going to get 156 kilojoules. Now, the question says calculate the heat liberated. So it gives it as a negative. So if you were writing as delta H, the change in energy of this reaction, it would be negative 156 kilojoules. Because this is the amount of heat released as a product. And if you say released as with words, then the viewer will know. But if you're going to use just symbols, you have to tell the viewer this change in energy, the release by a negative sign of a delta H. So that's why when you look at this example, there's a negative there. They're using the symbols that we use instead of words. Okay, the second question says, what mass of aluminum oxide must be used to produce, okay, there's a typo in there, to generate 250 kilojoules. So this time, what are we given? We're given 250 kilojoules, and there's a dot there, so that tells us that's 3 sig figs. And the question is how much aluminum oxide? All right, once again, start with what you have. I have 250 kilojoules. When you look at this, you will see them with the negative sign because they're using the delta H term. If I do that, my brain will get confused. But I'm going to know at the end to put this in the right terms. So I don't have to convert this to moles. That's one of the nice things about the energy. You go straight to the identity switch step. So my identity to moles of aluminum oxide, it's 3347 per 4 moles of aluminum oxide. Now, the question does said what mass of aluminum oxide, and I should have put this in my question mark, right? So I have to go through the conversion. And according to the slide, it's 102 grams per mole of aluminum oxide. There you go. Now you just do the math. 250 times 4 times 102 equals, divided by 3347. And you end up with 30.5 grams of aluminum oxide. This is 3 sig figs because there's a dot there that says, yes, it's definitely 3. 4 sig figs, 3 sig figs. So the answer isn't 3 sig figs. Okay. Okay, last question. A little more complicated. Again, I'm just going down the slides in the lecture slides. So the statement is burning 87.2 grams of C4H10 released delta H is negative 450 kilojoules of energy. Okay? That's the symbols for the words I just said. Put this energy into the balanced reaction. So the reaction you would be given, the skeleton reaction, is a typical combustion. And so we have C4H10. Again, I'm going to skip phases just for space limitation. So you have to balance this equation. So I suggest you try it, pause this, balance the equation, and then see if you get what I'm about to write down. Because this is a great practice one. Okay, so it's 2 hydrocarbon, 13 oxygen, 8 carbon dioxide, 10 water. So let's go back up to what we were given. First of all, I have grams of C4H10. I need moles. Just right off the bat, I need moles. Before I even go further, I need moles. Like, I'm not even going to think about where I have to go with this problem until I put that in moles. Okay, I want to put it in a form I can work with. And this is according to the slide. All right. So we have, this is 1.50 moles, 3 sig figs. Okay, now what do we do with this energy? We have this much energy released for this amount of hydrocarbon. Put it in a per mole. So how do you put this in? You want to put it in this reaction equation, but you need to put the exact amount. This is for the specific amount of hydrocarbon used. You want to put your energy in here for this molar relationship. So first of all, you start with you have 450 kilojoules per this amount of hydrocarbon, but we figured out it's 1.50 moles. So this will give you energy per mole, but I have 2 moles, right? In my reaction. So this is the energy per mole that was figured out by the data. This is lab data. Right? You got lab data, and now you're going to put it into your reaction equation, because you measured the amount of energy that came from consuming this much hydrocarbon, and now you're going to put it in this general reaction equation. So again, we're going to cancel out units. So my moles of hydrocarbon will cancel out. 2 times 450 divided by 1.5 will give you 600 kilojoules. Because that's the unit we're talking about energy. So that's the unit we want to keep with. So for the reaction, because this is your relationship, and then we had to use this equation to say, okay, that's the specific relationship, but for each 2 moles, how do I put it in here? So it's 600 kilojoules for every 2 moles of hydrocarbon, because that's what you have in your relationship, which means that's what you can now put over here. Your delta H for the reaction, because you were told that as a delta H is 600 kilojoules. okay? And to put this in the reaction, because we said, well, what about for 2 moles? Because that's what we have. All right, I'm going back to this. Since I did that, I can say plus this reaction released 600 kilojoules of energy. And I know that seems kind of confusing. Work it through a few times. I think there might be others in the book, or you can even just work this one a few times. But what you're doing is you did a combustion reaction. You found out when you burned this much hydrocarbon with oxygen, you released 450 kilojoules of energy. So that's a specific amount, but you can get an amount per mole, energy per mole that you did. And remember, once you have moles, we can put it in a reaction equation. So you got the amount of energy per mole. If I had stopped here, just this right here becomes 300 per 1 mole of C4H10, okay? I get that definition. And then I said, all right, and in this reaction, I have 2 moles of C4H10. Therefore, I have 600 kilojoules released. So that's how, if you have energy data that you got from the lab, this is how you calculate how to put it into a reaction equation. Okay, so practice it. Just like everything else we've been covering, the more you do it, the more comfortable you get with it. This one you might just have to go back and do occasionally to get back in your head how to do it. It's just because it's a little more unusual and we don't work with kilojoules that much. So, you know, once every 3 days, go back and do a problem like this or do this problem. Because the layout will be the same for every other problem like this. The numbers will be different. Your molecule might be different, but the layout is actually going to be exactly the same. So if you get to where you can do this every 3 days without thinking about it, you'll be able to do every other problem like this without any problem, because the layout's the same. It's just the numbers will be different, the molecules will be different, but everything else is, the concept's the same, the layout's the same. Okay, so that is the end of Lecture 11, Part 2. The last lecture will be Part 3, and that is going to be limiting reagent. It's going to be in its own lecture.